Hello there, bright minds. Did you ever wonder why a prism can turn plain white light into a rainbow? Well, it all starts with understanding what a prism really is. Picture this: a prism is a transparent object with flat, polished surfaces, kind of like a fancy piece of glass art that bends or refracts light passing through it. The key geometry here is the angle between two of those flat surfaces, which we call the angle of prism, or simply capital A. Now, when a beam of light strikes one of these surfaces, it bends at the boundary in a process called refraction, changing direction as it enters the prism. Then, as it exits the prism from the other surface, it bends again. This bending causes the outgoing or emergent ray to deviate from the original straight line path of the incident ray. The total amount by which the light changes its direction, the deviation, depends on three important angles: the angle of incidence, denoted as I, which is the angle the incoming ray makes with the normal at the first surface; the angle of emergence, denoted as E, which is the angle at which the light leaves the prism; and our very own angle of prism, A. Inside the prism, the path of the light ray is governed by the prism's refractive index, symbolized by the Greek letter mu. This refractive index tells us how much the light slows down and bends inside the material. Importantly, at both interfaces, the first and second surface, Snell's law applies. This law relates the angles and refractive indices at each boundary, ensuring that the bending of light follows precise, predictable patterns. So, just like a GPS for light, Snell's law guides the ray through the prism's geometric landscape, making all the angles and bends fit together perfectly. Understanding this basic geometry and terminology lets us dive deeper into how prisms manipulate light to create stunning optical effects. So next time you see a sparkling crystal or a beautiful rainbow, think of the simple yet elegant dance of angles and refraction inside a prism. Alright, let's zoom in on how light actually journeys through a prism and what happens at each face. Imagine a light ray hitting the first face of the prism at an angle of incidence, which we call I. According to Snell's law, the refractive index mu equals the sine of the angle of incidence divided by the sine of the angle of refraction inside the prism at the first face. Let's call that R1. In simpler words, mu equals sine I over sine R1. Because glass or any transparent material is denser than air, the light bends toward the normal as it enters the prism, a bit like a car slowing down and turning tighter into a bend. Next, the light travels inside the prism and reaches the second face where it exits back into the air. Here, Snell's law again tells us that nu equals sine of the refracted angle inside the prism at the second face, which we denote R2, divided by sine of the angle of emergence E. So, nu equals sine R2 over sine E. This time, light bends away from the normal since it's speeding up, going from denser glass to rare air. To describe the prism's shape precisely, the angle of the prism relates closely to the two refracted angles inside the prism, R1 plus R2 equals A. Finally, the total deviation delta, which measures how much the emergent ray has turned away from the straight path, connects to the incident angle and the emergent angle with this neat formula: delta equals the sum of I plus E minus the angle of prism A. Picture the ray's journey like a thrilling zigzag, bending in and then bending out, resulting in an overall change in direction that depends on these angles and the prism's geometry. This understanding forms the foundation for measuring and using prisms in all sorts of optical applications, from spectacle lenses to complex spectrometers. Now, here's a fascinating twist that makes prisms even more useful: the condition for minimum deviation. You know how sometimes you adjust a mirror just right to get the brightest reflection? Prisms have a similar sweet spot. Minimum deviation, which we'll call delta sub m, happens when the path of light through the prism is perfectly symmetric. That means the angle of incidence I equals the angle of emergence E, and inside the prism, the refracted angles R1 and R2 are also equal. When this symmetry occurs, the prisma's angle A simply equals twice the refracted angle R, so A equals 2 times R. Because the ray takes this balanced path, the formula for minimum deviation delta sub m becomes 2I minus A. And here's the golden formula connecting refractive index nu to the minimum deviation. Nu equals sine of open bracket a plus delta sub m divided by 2 close bracket divided by sine of a divided by 2. In plain words, nu is the sine of half the sum of angle of prism and minimum deviation divided by the sine of half the prism angle. This formula is not just a math trick, it's a powerful tool. Scientists and engineers widely use it in prism spectrometers to find the refractive index of materials precisely and identify substances based on how much they bend light at the minimum deviation point. Think of it like tuning a guitar string to the perfect pitch. When the light's path is just right, the prism reveals secrets hidden inside materials. Let's see how this all comes together with a quick example. Suppose we have a prism with an angle of prism A equal to 60 degrees and the minimum deviation delta sub m is measured as 40 degrees. Using our nifty formula, the refractive index nu equals sine of open bracket 60 plus 40 degrees divided by 2 close bracket divided by sine of 60 degrees divided by 2. So, we calculate sine of 50 degrees over sine of 30 degrees. Looking up these sine values, sine 50 degrees is approximately 0.766 and sine 30 degrees is exactly 0.5. Dividing 0.766 by 0.5 gives us about 1.532. This value means the refractive index of the prism material is roughly 1.53, very reasonable for a common type of glass. So, just by measuring the angles and the light's deviation through the prisma, we can uncover the prisma's optical fingerprint, giving us insights into what it's made of. It's like being a detective but for light. Now, let's add a splash of color to our discussion, literally. Prisms can do more than just bend light, they also separate it into its colors because the refractive index mu actually depends on the wavelength of light. That means blue light, which has a shorter wavelength, bends more than red light, which has a longer wavelength. This difference in deviation angles creates the beautiful spectrum we see from rainbows or through a prisma. The angular dispersion, which we'll call theta, is defined as the difference between the deviation angle of blue light, delta sub b, and that of red light, delta sub r. This angular separation explains the spreading out of colors. For very thin prisms, the total deviation delta can be approximated as the product of the difference between nu and 1 multiplied by the prism angle A. In other words, delta roughly equals open bracket nu minus 1 close bracket times A. To understand how efficiently a material spreads light into its colors, we use a term called dispersive power, symbolized by omega. It is calculated as the difference between the refractive indices for blue and red light divided by the difference between the refractive index for yellow light and 1. Mathematically, omega equals open bracket nu sub b minus nu sub a close bracket divided by open bracket nu sub y minus 1 close bracket. This parameter tells us how well a prism can spread white light into its component colors, a critical factor in designing spectrometers, cameras, and even fancy eyeglasses. So, that vibrant rainbow you see isn't magic, it's physics, with prisms playing the star role. To wrap it all up, let's recap the key ideas about light refraction through a prism. The refractive index mu relates the angles at the first phase by mu equals sine of incident angle I divided by sine of refracted angle R1, and at the second phase by mu equals sine of refracted angle R2 divided by sine of emergent angle E. The prism angle A is the sum of the two refracted angles inside the prism, A equals R1 plus R2. The total deviation delta, which measures how much the light bends overall, equals the sum of I plus E minus A. When the minimum deviation delta sub m occurs, the path is symmetric with I equals E and R1 equals R2, and the formula simplifies to mu equals sign of open bracket a plus delta sub m divided by 2 close bracket divided by sign of a divided by 2. For small angle prisms, a handy approximation is that total deviation delta equals open bracket mu minus 1 close bracket times A. We also learned that dispersion, the spreading of colors in a spectrum, arises because the refractive index mu varies with wavelength lambda. And finally, the dispersive power omega, defined as the difference in refractive indices for blue and red divided by refractive index of yellow minus 1, quantifies the efficiency of a prism's color separation. This knowledge is fundamental to understanding not just prisms but the behavior of light in many optical instruments we use every day, from cameras to spectrometers. That's all for today's concept. Physics is truly fun when you can laugh and learn together. See you in the next session.